So let's take a look at number 43 here in section 1.4. It says show that if A is invertible and AB equals AC, then B equals C. So let's do that part first of all. So if A is invertible, then what do we know? We know that its inverse exists, and we can call that inverse, right, A superscript -1. This is A inverse, right? That's the notation we used. It was previously proved, right, that if A is invertible, then its inverse is unique, and so that's the notation we use for that. So this exists, and we know that A inverse times A is equal to A times A inverse. Notice that we can commute that multiplication, and both products are equal to the identity matrix. So if I look at 43 then, and start with, so if we have AB equaling AC, then I can multiply by A inverse on the left, all right, both sides of this equation. Notice because this product AB and this product AC are both defined, and we said A is invertible, so it's a square matrix, then these these two products are defined. Yeah. And so the number of columns on A has to match the number of rows on B and C. Okay, but we can not commute multiplication, but I can reassociate, in other words, or group. So when I look at this product, I can regroup this as A inverse A times B, and over here I can regroup this as A inverse A times C. Now what do we know about A inverse times A? Well, we talked about that. That's the identity. So this right here is the identity, and this right here is the identity. So I have the identity times B equals the identity times C. But the identity times any matrix is the matrix itself. So IB is B and IC is C. And that is what we were trying to prove, that if AB is equal to AC, then B is equal to C. So that proves the first part. Notice that's only true if A is invertible, right? Because then this A inverse exists and I can multiply it by it. And so why, though, in part B, why is the example that they give in this book, why does it not contradict this? Because the example in the book gives an example where AB is equal to AC and B is not equal to C. We'll just go back to that example 3 real quick here and show you that. Right. So here's 3 matrices, A, B, and C, all the same size. And if I multiply AB times AC, or sorry, if I multiply A times B, excuse me, and A times C, I get the same matrix. And I will ask you to verify that on your own. All right? So A times B, this matrix times this matrix in that order, and A times C gives you the same result. But clearly, B and C are not equal to each other, and A is not the zero matrix. Okay? So the cancellation law does not hold up. So why does that contradict what we just proved? We just said that if A is invertible and AB equals AC, then B equals C. Well, no, it doesn't contradict it because A is not invertible in that example back there. So going back to this example, this matrix A is not invertible. There is no matrix that I can multiply this matrix by and get the identity matrix. And that should be pretty clear because if I get the identity matrix, I need a 1 in the upper left-hand corner of the matrix. And if I multiply any matrix by this matrix, so the row will get multiplied by this first column. So whatever the first row is, it doesn't matter. And when I multiply with this first column, I'm going to get 0 times 0. There's going to be a 0 up there, not a 1. Okay. And if I'm multiplying on this side, this row has a 0 in the first location. So when it multiplies times that entry there, we're going to get 0. And same with the second row. So it's not possible. Another way you can see that is with the formula for the inverse of a 2 by 2 matrix, right? And so if A and C are both equal to 0, as they are in that example, this is the formula that gives you an inverse. And in that case, A being 0 and C being 0, these two products are 0, their difference is 0. I've got 0 in the denominator, which can't be, right? Obviously you can't divide by 0. So the matrix is invertible only if this is true. AD minus BC is not 0. So that matrix, going back in the example, is not invertible, and therefore the cancellation law does not apply.